All right, thank you for joining MEPS Connect, and let's go through this last discussion sheet here. And thank you for subscribing. So the first question is asking us to find for absolute maximum and minimum. And as we know, anytime we want to find absolute maximum and minimum, first we need f prime. Then we use f prime to find the critical point, and we check if our critical point is in the domain, and then we use the table to find for our absolute maximum and minimum, if any. So let's go through the process together. Now here, what we are going to do here is, now we have f of x, which is equal to minus x, which is equal to minus x to the power 3 plus 3x squared minus 5. So what do I need first? We need f prime of x, which is going to give us minus 3x squared plus 6x. So this is what you are going to get. Now I can factor minus 3x out and have x minus 2. So guess what will be the critical point? Critical point is going to be x is equal to 0 and x is equal to 2. So that will be the critical point here. So after the critical point, we need to check if our critical points are in the domain. So now the domain is 1 and 3. So 0 is not in 1 and 3. So it means that here we are going to take 0 out, but 2 is there. So now for us to find absolute maximum and minimum, we need to have our table. I put my x value here, but first I will use the endpoint. And then since 0 is not in between this, we have 2 in between 1 and 3. So now I need my f of x here. So I need f of 1, I need f of 2, I need f of 3, which is equal to this. Now plug in 1 inside this function here. What we get? 1 to the power 3 is still 1 plus 3 minus 5, and this is going to give us minus 3. Plug into 2 to the power 3 is 8 plus 2 to the power 2 is 4. This is going to be 12 minus 5. And then when I add this, is going to be minus 13. So this will be minus 1. And then let's plug in 5. Okay, this one's supposed to be 3. 3 to the power 3 is 27. And then 3 squared is 9 plus times 3 is 27 minus 5. And this is going to give us minus 5. So we can see that the max is going to happen here, and then the minimum is going to happen here. So that's all we just need to do here. So absolute maximum equals minus 1, and absolute minimum is equal to minus 5. Yeah, so the first question is simple. It's going to get exciting. So now let's look at this question here. Now here the function is this, and we want to find the increasing and decreasing interval. So the process that we use to find local maximum and minimum, that's the same process that we are going to pass through to find the increasing and decreasing. So the first thing that we need to do here is we need to find the critical point. So let's do that. We need f prime. So f prime here will be 4x to the power 3 minus 12x squared. Now let's try and simplify this in half. I can factor 4x squared out. So I'm going to have x minus 3. So now we can see that when x is 0 and when x is 3, we have our critical points. So now I can shift this guy here. And then now that we have our critical point, we can just put it on the normal line so that we can find our increasing and decreasing interval. Don't forget here we use the f prime, and then we use the critical point here. So the critical point with f prime. So this is going to be 4. So now let's try and work out here. So plug in -1 in this, and let's see what is going to happen. So when I plug in -1, so let's look at this one here. So -1 is going to be 4 positive, because 1 squared minus 1 squared is positive, and in here is going to be minus. So this is going to be minus, and everything will be minus. So this is going to be minus, and this one will be decreasing. Plug in 1. Already this is positive, so it's going to be positive. When I plug in 1 here, still this is going to be negative. So still I have negative here. So I still have negative, and this is going to decrease. Plug in 4. This will be positive, and then positive again, because this will be positive, and this one too will be positive. So now this is now going to be positive, and this is going to be increasing. So now let's write the increasing and decreasing interval. So increasing interval will be now from 3 to positive infinity, and then the decreasing interval will be from minus infinity to 0, and then from 0 to 1. So that will be what we are going to get from here. Very simple from there. Now we need to check for concave up and down. So concave up and down too, we are going to use a sign chart, but here we need f prime prime. So now let's continue by differentiating this one again. So differentiate this again, and we are going to have 12x minus 24x. Then we need the values that will make this one 0. So I can pull out 12x out and have x minus 2. So here we are going to have x is equal to 0 and x is equal to 2 to make this one 0. Then we can now think about our concave up and down. So let's use a sign chart here. I have 0, I have 2. Here we are using f prime prime of -1, f prime prime of 1, and f prime prime of 4. I'm not using 3 because 3 is a critical point. Now plug in -1 in this. What happened? When I plug in -1 here, this one will be minus, so it's going to be 12 minus. And when I plug in -1, this one too will be minus, because I have this one here minus minus. So it's going to give us positive. So this will be positive, and we know that positive is concave up. Now let's look for 1, 12. This will be positive, and this is going to be negative. Yes. So this is minus, and this is going to be concave down from here when you plug in 1. Last one is 4. This one will be positive. This one too will be positive. So this is still positive, and this is up. So concave up interval is going to be minus infinity to 0, and from 2 to positive infinity. Concave down interval is just going to be from 0 to 2. So that's what we are going to do from here. And let's look at question 3. Now, question 3, we want to get the increasing and decreasing interval, but we need to pay attention here. We see that this one, instead of them to give us gen of x, they've given us gen prime of x already. So we just need the critical point. So here, gen prime of x is already equal to x plus 3, x squared plus 1 e to the power x, right? So look at values of x that will make this one 0. So 1 is when x is equal to -3. But this one cannot be 0 on the real line, right? Because we cannot make this one 0, this one too. So the only point here is x is equal to 3. So now we put 3 here, and then we pick anything before -3 and after -3. plug it in. Let's try it and see. Plug in minus 4 here from the first start. This is going to be minus 4 on the second parenthesis will be positive. This one to be positive. When you multiply it through, you are going to get a negative. So this is going to be decreasing. Now, last one is now pick minus 2. Minus 2 here will be positive, and this one will be positive, this one will be positive. So this will be positive, and this one will be increasing. So increasing interval is going to be from minus 3 to positive infinity, and decreasing, and the decreasing interval is going to be from minus infinity to minus 3. Now let's check local maximum and minimum from this. So we can see that we have this, right? Negative, positive. So this is going to be giving us local minimum. So local minimum at x is equal to minus 3. So here we can see that no local maximum. That's what we are going to get from here. Okay. Now let's look at question 4, which is interesting. So question 4 is we want to sketch the graph of, f of x given the following function. So if you remember what we just did here, we did something like increasing and then concave up, which is the same as the local maximum and minimum. And increasing and local maximum and minimum, we were using f prime, and concave up and down, we were using f prime prime. So let's use the same idea here. Now we are going to use all the functions with f prime. So let's circle the function with the f prime. So these functions are with f prime. This one too is also with f prime. So now let's put it on the normal line and see what is going to happen here. So let's look at the interval here. We have this interval, this, and this. So we can see that the values in here is minus 1, 2, and 2. So we can pick minus 1 and 2. So we have interval from negative infinity and then up to positive infinity. So we have interval this, which is here. We have from minus 1 to 2, which is here. And we have from 2 to positive infinity, which is also here. But we see that from negative infinity to minus 1 is less than 0. Anything less than 0 is negative, so this is decreasing. Now, in between minus 1 and 2 is greater than 0, so anything greater than 0 is positive and also increasing. And then this one is indeed also decreasing because it's less than 0, so this is minus, and this is also decreasing. So we're able to get to this. Now, let's also pick the ones with f prime prime. So let me just circle the ones with f prime prime with pink. So let's use the f prime prime. Let's draw the number line here. And let's look at the interval. So we have negative 1 and we have 3. So let's do that. So negative 1 and 3. So I put negative infinity here, I put infinity here. So in between negative infinity and 3, this is less than 0. Less than 0 means that it's negative, and when it is negative, we have concave down. In between minus 1 and 3, we have less than 0, and also negative, we have concave down. In between 3 and positive infinity is greater than 0, so it's positive, and we have concave up. So we've made use of this information and this information. So now, before we draw the diagram, let me combine these two, concave up and increasing and decreasing here. Combining this, we have from negative infinity to minus 1 to 2 and to 3 to positive infinity. So I'm just combining this and that. Now what is happening here? Let's see. Now what is happening here is from minus infinity to minus 1, which is this is increasing. This is decreasing. But at that place, we have concave what? Concave down. So here, because this is decreasing and we have concave down, we are going to focus on this aspect. We are going to focus on this aspect. So we are interested in this so that it goes with this one. In between -1 and 2, the function is increasing, and we have concave down, which is between this and 2, because 2 is also in between here. So since the function is increasing, we are going to also focus on the increasing part of this function. We are going to focus on this part of the function so that you go in this one. Let me use different color for this so that I will see that I'm using the red for the graph. Now let's look at in between 3 and 2 and 3 is increasing because it's also here. So this is decreasing, and in between 2 and 3 is still here, which is also concave down. And since it's going to negative, we are going to use the negative side here. Now let's look at after 3 to positive infinity. 3 to positive infinity is also here, still decreasing. And here we have concave up. So since we have concave up here, and this function is decreasing, we are going to look at this tail here. So we are going to use this one here. Now let's combine everything together and let's draw the graph. Very nice. Now looking at the information, one, we see that at A, so let me use orange. A, -1 is a vertical asymptote. So at -1, we have a vertical asymptote. So let's draw that one first. Now the critical point, we have 2, and then we have 3. So at 1, we have vertical asymptote. So this is done. At x is approaching negative infinity, here we are approaching 1, and positive infinity 2, we are approaching 1. So we have a horizontal asymptote. So let's have a horizontal asymptote at 1. So this is where x is equal to, let me use different color for that. This is where x is equal to 1 here. That's where the x is approaching infinity, or it's not approaching infinity. So now let's try and combine the graph. So I have already done this one here. Okay, let me use orange for that. I've already done this one here. So what is happening? When x is approaching negative infinity, we need to approach 1. So when x is approaching negative infinity, we should be approaching 1 here. So when we are moving up, we should be approaching 1. Let me use different color for this one, diagram here. Okay, I think the light green is nice. So we'll be approaching 1, right? So as x is approaching negative infinity, this one should be 1. So we are done with this one. Let me take this one, and we are done with this one too. But what is happening when we are approaching 1 on this interval? We see that at 1, let's look at the graph that we combined here. At -1, the graph is the one which is red. So this is approaching this, right? It's decreasing. So it means that this is going to be like this. And since -1 is a vertical asymptote, it cannot cross. So this is how the graph is going to look like. So we are done with this one too. Let me take this one. Now let's plot this and this. F of 2 is 3. So let me assume that I have 2 here and I have 3 here. F of 2 is 3. So I'm going to have my 3. I'm going to have my 3 here. And then f of 3 is 2, and I'm going to have my 2 here. Nice. So we are also done with this. So let me take this one. Now, let's try and see what is happening. Now, f of 0 is 0. Let's plot f of 0 is 0. F of 0 is 0 is going to be here. So it means that the graph is going to touch the graph is going to touch it's going to pass through the origin. So let me just do this one well. Good. So let me have my 2 here, and let me have Let me adjust this one too here. Good. So now we are done with this one too. Now let's try and combine the graphs. Now remember, at f prime prime of 3 is 0 and f prime prime of 2 is also 0. So now let's see what we can do here. Now looking at this graph here, after -1, the graph is increasing and it increased up to 2 and start decreasing. So it means that now the graph from here, we are going to have something increasing up to 2. Oh, this is not nice. Great. Oh, why? Why am I not passing the origin? Okay, good. This is passing the origin now. Yeah. So, but don't forget, at 2 we have maximum, right? At 2 we have maximum. So it means that that's the reason why this goes up and start decreasing, because we have maximum. So at 2 we will start decreasing here at 2. After 2 we start decreasing. But after 2, as we are starting decreasing here, the function will continue decrease, right? It will start decreasing again. So it will just be decreasing. But we also see that as x is approaching positive infinity, we need to be approaching 1. So let's take 1b because we are done with that. So as we are going to positive infinity, we should be approaching this line here, which is 1. This is where x is equal to 1. So we are done with this, we are done with that. And then combining this, and this is the one that was helping us to draw this graph here. So this is what you are going to get for the graph. But let's look at something here. F prime of 2 is 0. So f prime of 2 is 0. So what should we do? F prime of 2 is 0. Okay, so f prime of 2 is 0. It means that here is constant. So when I differentiate it, I should be getting 0. That's why f of 2 is 3. So when I differentiate this, I get 0, which is true. And then when I differentiate f of 3, 2 times, I'm going to get 0. So that one too is true. So this is how the graph is going to look like. This is how the graph is going to look like. There's a lot of analysis to do. Now let's look at question 5, which I also like. Now question 5, don't forget, I think the function here should be g of x, but yeah, so this one should be g of x. This one should be g of x. So we have g of x graph, right? And don't forget, this y here is the same as g prime of x, as we have indicated here. Now, anytime you have derivative, the first derivative graph, think about this. Anything above the graph is greater than 0, and anything below is less than 0. And anything on this line here, is when g prime is equal to 0. So we have 3 things here. On the line, that's when g prime is 0. And I know that anytime g prime is 0, that's when we have the critical values. Good. And then anything above is when we have, maximum or increasing. And anything which is less than 0 is when we have decreasing. So let's put that one in mind, which will help us to analyze this. It means that the graph that we have, anything above this line is basically increasing because it's greater than 0. So this, as coming to this up to this, is an increasing because it's above. So let me just use blue line to show you. This up to this is increasing, and this is also increasing because it's above the x-axis. And the one which is the orange is below, so decreasing, right? So this is decreasing, and then the one which is blue is increasing. This is wonderful. So now the question is asking us to find the increasing interval. So let's see how we can write the increasing interval. Good. Now increasing interval here is going to be, now look at this. Remember, anytime this is equal to 0, this is what? Critical point. So let me now clean the board so that you will see what is happening here. Now when I clean this, since now we know, we see that at 1, the graph touches this one at 1. So at x is equal to 1 is a critical point. This is also a critical point because the graph also touches here, and this is also a critical point. Critical point, critical point, critical point. So it means that if I want the increasing interval, I'm going to increase from minus infinity up to the critical point here. Because we are using the critical point, we use the critical point to write the increasing and decreasing. Up to minus 1, and then another increase from minus 1 to 1, because it's still above the graph, minus 1 to 1, and then last one is from 3 to positive infinity. From 3 to positive infinity. So that is how the graph look like. These are all above, and this is also above. Now decreasing interval, guess what will be the decreasing interval here? Decreasing interval is just the one below the x-axis from 1 to 3. So this is going to be 1 to 3. That's nice. Now the question is also asking us to find the local maximum and minimum. Now don't forget, with local maximum, remember when we are using a sign chart, if we are looking for local maximum and minimum, let's assume that we have 0 here and 2 here. Remember, local maximum happens when we have positive, negative, right? Let me write it well for you to see. So positive means that this is increasing, and negative means that this is, and positive means that this is increasing. So if we have something like positive, negative, then we have maximum. And if we have something like negative, positive, then we have minimum. So now let's see what is happening here. Remember, anything above here is increasing. So I can say that from this up to this with the blue is positive because it's above the x-axis. It's positive. Now, anything below here is negative. So what is happening here? Now, remember, when we are reading it, we need to read it from the left to the right. So we have negative to positive. When you have negative to positive, what do you have? Local minimum. So we have local minimum, which is at x is equal to 3. And remember, I should have written the critical point. So the critical point, they didn't ask us, but let me write it here so that it will help us. Critical point is x is equal to minus 1. Oh no, we cannot, let me just take it out. I shouldn't talk about critical point right now. So that is what we have here, right? But now let's look at what is also happening here. Now we have here also, it's also minus, right? And this is above, also plus. So anytime we have positive, negative, we have maximum. So the value in between them is 1. So local max is at x is equal to 1. Now let's look at what is here. Now what is here, we can see that, let me use red. This is, don't say that this is decreasing. This is not decreasing because it's above. This is positive. And then after 1, 2, from here, let me use different color here. From here to the function is still positive because it's above, right? And this, the sign is not changing, so we cannot say that it's what? It's a maximum or minimum, right? So this is what we are going to get for the local max and minimum from here. Now, on what value is f of x concave up or down? Great. So now for us to talk about concave up and down, now think about that. Now for us to talk about concave up, we need to think about this function as f, and you are looking for f prime. Then if it is increasing, it goes like this, and if it's decreasing, it also go like this. So now because this graph here is g prime, and we are looking for g prime prime because we are looking at the concavity, then the assumption of this changes. Now we change our perception from thinking this way to Now thinking this way. Now we are thinking that anything that is coming down is decreasing. So now this is decreasing. Now this is decreasing. This is increasing. This is decreasing. This is decreasing. This is increasing. So that's basically our assumption now. So now let's see what is happening here. Now remember, for us to talk about this concave up and down, we need the point that will make the second derivative zero. What are the points that is going to make the second derivative zero? The point that is going to make the second derivative zero are the one that is going to be the minimum and maximum. Because don't forget, this is the f prime. Now let's think about this. If this one was f of x, y is equal to f of x, then if I ask you to find the critical point, you are going to tell me that that is when the function is having its maximum, the function is having its maximum, and the function is having its maximum. So if we are moving from f of x and we are at f prime, then when we go, now the function changes, right? Good. So now we have g prime of x. So here the point that will make the f prime prime or g prime prime 0 is the one that we have minimum, maximum, minimum. So this is going to be minus 1, 0, and 2. So that is what is going to give us the, let me call it point of inflection, even though if you have not gotten it, right? So that's where the sign changes. That's when it changes from whether it being positive or negative to the other sign, right? So that's basically what is happening here. So now let's see what happens here. What is happening after minus 1 or before minus 1 is decreasing. This is decreasing. So we have shit our mind. So this is decreasing. And then after minus 1, oops, when it is decreasing, remember this is concave up and down. So when it is decreasing, when it is minus, we have concave down. Now, after this one, we see that the function is increasing. So we have positive and we have concave up. Then after 0, which is here, the function starts decreasing again. We have minus, we have concave down. And then before 2 is still minus, and after 2 is increasing. So we have positive and we have concave up. So this is what we are going to get from here. So now what will be the interval? So we are looking for the interval. So concave up, interval. This is going to be concave up is going to be minus 1 to 0 and 2 to positive infinity. And then concave down interval is going to be minus infinity to minus 1 and 0 to 2. So this is what you are going to get from there. And the question is, do we have point of inflections? Yes, we have them. We have point of inflection. So point of inflection is going to be x is equal to minus 1, 0, and 2. Why? Because all of them are changing sign. Positive, negative, positive, negative, positive. So all of them are point of inflection. So that is the idea here. Now, if the question asks you to find a critical point here is going to be x is equal to 1 and x is equal to 3. Now, you see, this is not a critical point because it's not changing sign. This is positive and this is positive when you are talking about the f prime or g prime direction. This is positive and this is positive. So we can't call it a critical point, even though that is when g prime is equal to 0. But it's not equal to 0 because this is not changing. That's why minus 1 is a point of inflection. Okay, so that is that for question 5. And let's look at question 6. A farmer has 750 feet of fencing. He has to build a fence enclosing a rectangle region and then divide the area into 4 pens in a row. Okay, so let's see, we have rectangle here. So rectangle, we have this And then we have this, right? Let me actually change this one to this. So I have my nice rectangle here. I have my y, I have my y. Now I want to divide this one into rows, right? Now, how many? 4. Yeah. So 1, 2, 3. And these rows that we are doing now, this is x, this is x, this is x, this is x, this is x. So that's basically what we've done here. And we are saying that if we are fencing all these things here, it's going to cost us this. So it means that we are going to have 4x plus 2y is equal to 750 from this. And we want to, find the dimension of the region that enlarges the area. So what is the area of a rectangle? Area of a rectangle is equal to xy. So here we can make one of them the subject and we just plug it in. So let's make y the subject here. 2y is equal to 750 minus 4x, and then y will be equal to 750 minus 4x divided by 2. So let's do substitution here. Now our area is x times 750 minus 4x divided by 2, and this is the same as 750x minus 4x squared divided by 2. So this should be the area. Now because we want to find the dimensions, then we need to take the first derivative and then look for our x values and verify if it's indeed the dimension. So now let's find for f prime, a prime, but don't forget this is the same as 1 over 2 times 750x minus 4x squared. So this is just a constant. So a prime here will be equal to, I have my constant, differentiate what is inside, and we are going to have 750 minus 8x. Good. So now let's try and see if we can set this to 0. So setting this to 0, we want to look for value that will make that this is equal to 0. So 1 over 750 minus x should be equal to 0. 750 minus 8 is equal to 0. Because if I multiply this one by 2, multiply this one by 2, this will be 0 and this one will be 1. So we have this one here. And then what can we do again? Now we can have 8x, which is equal to 750. And this is going to be a little bit crazy, but let's see if we can break it down. 2 goes here, 4. 2 goes here. Let me see. 2 goes to 7. 3 goes to 15. 7. Okay, I've gotten this one here. Might do. Oh, okay. I think I'm not doing something right. The x supposed to be 5. Because 1, 2, 3, 4, 5. So our x should be 5. So this one should be 5. This one too should be 5. This one should be 5. This one too should be 5. And this one should be 5. So when I multiply through, when I take the derivative, okay, this one should be 10x. So 10x also here. So this one should be 10x. So let me just do everything here again. Okay. Oh, if 10x, then if I divide 2 by 10, then x should be 75. Okay, this job done. Okay, now let's find the domain. We can also find for the domain. Here, now we are dividing the function by 2, but remember 2 is just a constant, right? So it means that here our x should be greater than or equal to 0, y should be greater than or equal to 0, because it's not divided by x or y. So here, since y is greater than 0, then we can have 750 minus 5x over 2 to be also greater than or equal to 0, because this is y and it's the same as this. I can multiply through by 2 and I'm going to have 750 minus 5x greater than or equal to 0. Then move 5x or add 5x on both sides and we have this. Divide through by 5 and I'm going to have 150 is less than or equal to x. So the domain here is going to be from 0 to 150. That will be the domain. Good. Now we have gotten the x value, so we can decide to also find the y's value here. So what is y? Y is equal to this. 750 minus 5x divided by 2. So let's plug it in and see what we are going to get. So 750 minus 5 times 75 divided by 2. I guess what is 7 times 75? This is going to be crazy. Okay, let's do it quick. 25 to 35. Oh, 375 again. 375. Oops. 750 minus 375 divided by 2. So when you subtract, what we get? 750 minus 370 is 0. Add 1. This is 8. This is 6. And this is 2. Okay, 280 divided by 2. Is that right? I feel like what I'm doing is wrong. Okay, this one is supposed to be 5. So this should be 5. This one will be 4. Add 1. This is going to be 7. Okay, so and I think now 2 goes to this 187.5. Yes, so this is right. Okay, so we have our x and we have our y, but let's confirm it. Let's use the table to confirm it, right? Let's use the table to confirm that. We have our x, we have our a of x. What was the domain? Domain is 0, 1, 5, 0, and our x is 75. So plug in 0 inside a of x, plug in 75, and plug in 150. Most of the time, the endpoint is kind of like 0, right? Because now let's plug in 0 here. Yes, indeed. When I plug in 0 here, 0 here, 0 here, everything goes to 0. 150, plug in 150 here, 150 here. This one too also go to 0 indeed. And then here, what do we get? So instead of plugging it in, I can plug in it inside this one too. So this one will be x times y. So x is 75 and y is this. So when I do that, I'm going to have 75 times 176. And definitely this is going to give us the max here, right? So when you multiply it, this is going to give us the max. So yeah, this verified question 6 that we get the total area. Let's look at question 7. We are almost done. We have 3 more questions to go. 4 more questions to go. Now we want to look at the linear approximation, which is f of a plus f prime of a x minus a, right? So what do we think we need to do here? Now a is given, right? Which is this. So let's do direct substitution. This is equal to f of 0 plus f prime of 0 x minus 0. So what do we need to do? Now we need f of 0. But f of x is equal to tan inverse of x. So we need to plug in 0 and have tan inverse of 0. And what is tan inverse of 0? What is tan inverse of 0? So tan inverse of 0 I think it should be 0. So tan inverse of 0 is 0. Now before we get f prime of x, before we get f prime of 0, we need f prime of x. And this is the tan inverse. So when I differentiate this, I'm going to have 1 divided by 1 plus x squared. Then when I plug in 0, I have 1 divided by 1 plus 0 squared, which is equal to 1 divided by 1, and this is equal to 1. So let's now find our linear approximation here. F of 0 is 0. This is 1, x. So this is just x. This is just x. Now we want to use this to approximate the tan inverse of 0.04. So we want to approximate tan inverse of 0.04. Now compare this to this. And you will see that if I compare this to this, you will see that we have tan inverse, tan inverse. So x is what is inside the parenthesis here. So this one is approximately L of 0.04, which is equal to, this is equal to x. So we still get 0.04. So this is what we are going to get for the approximation here. 8. If f is continuous and differentiable everywhere, we have f of 0 to be this and this one to be this. Which value is guaranteed by the mean value theorem? That there is a c in between 0 and this, such that the slope this is equal to, okay. So now we are saying that here we have there is this c. Now this c is between 0 and 2, which was stated here, right? Now the mean value theorem states that this, if we have c in between this, then f prime of c should be the same as f of c minus f of b minus f of a divided by b minus a, right? So the mean theorem, if we have c in between a and b, so now when you compare this, we see that a is equal to 2, a is equal to 0, and b is equal to 2. So it means that f prime of c will be equal to f of 2 minus f of 0 divided by 2 minus 0. F of 2 is 1, f of 0 is 5 divided by 2. This is minus 4 over 2, and this is going to give us minus 2. So this is very simple here. So the slope of the tangent is minus 2 using the mean value theorem. Okay, last two questions, last but one, then we are done. Let's try and see if you can solve this. Okay, so this I think is good for us to use the L'Hopital's rule. So first, let's test this and see. Plug in infinity here. E to the power infinity is infinity. Plug in infinity at the denominator till we have infinity. So we can say that this is the same as L'Hopital's rule. Now let's differentiate e to the power e to the power x. When I differentiate it, I get the same thing again. Divided by, differentiate that down, we have 2x plus 3. Then plug in infinity again. The top will be infinity, down will be infinity. So we need to apply the L'Hopital's rule again. And then we have limit x is approaching infinity, e to the power x. When I differentiate 2x plus 3, I get 2. Now plug in infinity again, and this is going to be e to the power infinity divided by 2, which is infinity over 2, and this is infinity. So we are done here. So we are going to get infinity here. Now let's go to quick, because we are keeping long here. Plug in infinity here. The top will be infinity divided by infinity. Let's use L'Hopital's rule. Okay, limit x is approaching infinity. This is going to be 10x minus 7 divided by, when I differentiate e to the power 3x, I have 3 e to the power 3x. So now this is equal to, when you plug in infinity again, you get infinity over infinity. So another this again, differentiate the top, you get 10 divided by, differentiate the down and get 9 e to the power 3x. Now plug in infinity and you see that this is going to be 10 divided by e to the power infinity is infinity. Infinity times 9 is infinity. And 10 divided by a big number is a 0. So that's what you are going to get here. Now this one, we need to use the L'Hopital's rule, but we need to try to modify this function, right? Because L'Hopital's rule, we need to have a numerator and we need to have a denominator. So it means that we can write this one as limit x is approaching 0 from the positive, the natural log of 3x divided by, then I write the x squared as 1 divided by x squared. Now let's test it. When I plug in 0 here, this is going to give us infinity, because ln of 0 positive will be as positive infinity. And then this one here is also going to give us infinity, because when I plug in 0 here, this is going to happen from there. So now what happens here? Now we can apply the L'Hopital's rule. Now remember, when I differentiate the natural log of x with u, this is 1 divided by u times u prime. So this one is going to be limit x is approaching infinity or 0 positive. Now the top will be 1 divided by 3x times 3 divided by, now when I'm differentiating 1 over x squared, I'm thinking of x to the power minus 2. So differentiating this will be giving me minus 2x to the power minus 3. And I want to rewrite back, and I have this one minus 2 divided by x to the power 3. So this is minus 2 divided by x to the power 3. Nice. Now let's see if we can simplify this. So limit x approaching infinity or 0 positive. Now this will cancel this, so I have 1 over x times, then this will, okay, let me just do it, divided by minus 2 divided by x to the power 3. Then this is limit x is approaching 0 from the positive, 1 over x times, then now we have x cubed over 2. So what is going to happen here is, now we can cancel some terms out. X will cancel what is here. So this is going to be minus x squared divided by 2. And when you plug in 0, this is going to be just 0, right? This is just going to be 0. So that's what you are going to get from that one. Let's do this one, and we do the last question, which is question 10, then we are done. Now, anytime we want to find limit, and we have the base to be in terms of x, and this one to the power x, then we need to make sure that this is equal to L. And then we take the natural log of both sides. X is approaching infinity. Natural log of x plus 3 divided by x to the power x is equal to this. And because of this natural log, x can come down, and we are going to have limit x is approaching infinity, x here, and we have x plus 3 divided by x, which is equal to this. Now, we want to see if we can apply the L'Hopital's rule. So we need to write this one as a rational function. So limit x is approaching positive infinity, natural log of x plus 3 divided by this divided by 1 over x is equal to natural log of L. Now let's check and see what we can get here. Now, don't forget that the function here can be written as this can be written as x, this is the same as 1, this is the same as x over x plus 3 over x, which is the same as 1 plus 3 over x. So when I plug in infinity here, 3 over infinity is 0. So this one will be 1. Natural log of 1 is going to be 0. So this will be 0. Let me put it here. This will be 0 divided by, when I plug in infinity here, 1 over infinity is also 0. So indeed, we can apply the L'Hopital's rule. So now let's apply the L'Hopital's rule. Now L'Hopital's rule, I need to differentiate what is here. So the same thing as we did for the natural log, this is going to be limit x is approaching infinity. Now here we need to use the quotient rule to differentiate this. Aside we using the, so this is going to be 1 divided by x plus 3 divided by x times, then we differentiate this, right? But we know that this is the same as this, so we can think of this and just use what is here to differentiate. So this is, if this is the same as this, then this is the same as 1 plus 3x to the power minus 1. When I differentiate 1, I get 0, and when I differentiate this, I have minus 3x squared, x to the power minus 2, and this is the same as minus 3 divided by x squared. So I can just multiply this one by minus 3 divided by x squared. Now let's differentiate this, which is 1 over x is the same as minus 1. So when I differentiate this, I have minus x minus 2, which is the same as minus 1 over x squared. So everything here is divided by minus 1 over x squared, which is equal to the natural log of L. So now we need to play around this here. Let's play around here. Now this is the same as limit x approaching infinity. Now this is 1 divided by the whole of this. So I can swap it and have it to be x divided by x plus 3 for this one. Then times minus 3 divided by x squared divided by, so I can use this division as divided by here. So divided by a minus 1 over x squared natural log of L. So we are going through a lot here. This is the same as infinity, and here I can cancel one of the x, so I'm going to have 3 over x plus 3 times x. So when I cancel one of the x, it will be left with one of the x here, and there will be 3 here. And then I can change the division to multiplication and have it to be minus x squared, and this is equal to the natural log of L. Now what's going to happen here is I can cancel one of the x again, and the minus will multiply. So I'm going to have limit x is approaching positive infinity, minus cancel minus, one of the x cancel the x. So I'm going to have 3x divided by x plus 3, which is equal to this. We are almost there. Let's plug in infinity again. Put infinity here, and we are going to get infinity over infinity again. So I don't have space, so unless I continue from here, I'm going to continue from here. So when I plug in infinity, I get infinity over infinity again. So we need to use the L'Hopital's rule again. So got limit x approaching infinity, 3 divided by 1. And this is that. And then fortunate for us, limit of a constant is the constant. So this implies that we have 3, which is equal to the length of this, and e to the power 3 is equal to L. So now our solution here is equal to e to the power 3. So that's what we are going to get for the day. And let's finish by solving this derivative for question 10. Then we are done with this video. Now we want to find the derivative of this sine inverse. So as I said, this is like, what I gave the other time. So remember that if I want to differentiate sine inverse of x of u, this is 1 divided by square root of 1 minus u squared times u prime. So when I compare sine inverse to sine inverse here, I can see that my u is equal to the natural log of x, right? So when you compare this and this. So from the formula here, we need u prime. So u prime will be 1 over x. So here f prime of x will be equal to 1 divided by square root of 1 minus u squared. U is the natural log of x. So this will be this times 1 over x. and then we are done. Now tangent to, when I differentiate tangent inverse of u, this is 1 divided by 1 plus u squared times u prime. So here my u is equal to x to the power 8. I need u prime, right? So u prime will be 8x to the power 7. And then f prime of x will be equal to, so just use substitution here. I'm going to have 1 divided by 1 plus u squared. U is this, so I need to square this. 8 squared times u prime, which is 8x to the power 7. If you want to simplify, now this becomes 7 divided by 1 plus x to the power 16. So this is what you are going to get from this. Okay, we are almost done. And let's look at this one here. Now, for us to differentiate this one is like the L'Hopital's rule here, right? You know, we have a function to the power x. So we need to take the ln on both sides. So here we are going to pick ln of f, which is equal to ln of x to the power ln of x. So what can we do here? We can have ln of f, which is equal to, so because of ln of this can drop down. We are going to have natural log of x times natural log of x. Now we can differentiate it. We know how to differentiate a ln function, which is here. So 1 over u divided by u prime. So it means that this is going to give us 1 over f times f prime, which is equal to, now let's use product rule for this guy here. If a is equal to ln of x, what should be a prime? 1 over x. B is equal to ln of x. What should be b prime? 1 over x. So this is going to give us ln of x divided by x plus ln of x divided by x, because we need to multiply a to b prime and b to a prime. So we are almost there, right? We are almost there. So now we have f prime over f, which is equal to, now this and this are the same, so I can combine it to have this divided by x. And then now we are making f prime the subject because that's what we need. So this is 2 ln of x divided by x times f. But we don't want our final solution to be in terms of f. So we need to make sure that we replace f by what we had. So f is equal to this. So now our final solution, f prime of x, will be equal to 2 natural log of x divided by x times x to the power x. So this is what we are going to get for our C. And let's do the last one. There we go. So the last one also follow the same procedure. Just pick ln of both sides and then have ln of x squared plus 1, 3x. Then the ln function will help us to drop 3x. Then now we can start differentiating. So when I differentiate ln of f, I have 1 over f times f prime. Here I can use the product rule. So let's do that. A is equal to 3x. A prime will be equal to 3. B is equal to the natural log of x squared plus 1. So what should be b prime? Oh, b prime is going to be 1 divided by x squared plus 1. Then we differentiate x squared plus 1 and get 2x. So this will multiply this and this will multiply that. So we are going to have 6x divided by x squared plus 1. So I multiply this by this, which is 6x squared. Okay, it should be x squared. And then I have divided by this, plus this multiplies this, and we have 3 natural log of x squared plus 1. So we go through the same procedure again. F prime is equal to 6x squared divided by x squared plus 1 natural log of x squared plus 1 all times f. Then we need to replace f by this. So therefore, our f of x which is our final solution for the day, is going to be 6x squared over x squared plus 1 plus 3 natural log of x plus 1 times x squared plus 1 x to the power 3. So this is our final solution of the day. So we should be having something like this on it. Great. So this was a long journey and we are done. So I wish you all the best in your exams.